Okay, thanks for your introduction. Yeah. Hi everyone, I'm Helin. I'm now working with Najim, Loreno, Jesus, and Thomas. So I'm going to introduce my recent work, SoloAudio, that I work with Jerry Hai and we submitted to the ICAST 2025. So let's first give you a brief introduction of what can SoloAudio do. Here we have an audio here. Let me play it.
Are you ready to rock?
And there are some sounds within this audio, including people speaking and sound of the gunshot. If we want to get the sound of gunshot, we can use the SoloAudio to get it. Yeah, that's pretty cool, right? Another example, maybe if we have many music instruments and we can get, we want to get one of the music source from the, from the mixture musics, we can also use this model. This is the mixture audio. And we want to get the sound of the cowbell. So by using such a model, we can get a very clean source from a mixture audio. So what we did in this work is the target sound extraction. That is a part of the cocktail party problem that we want to extract the sound of interest from a mixture audio. Let's first go through the existing method. There are two popular ways, including discriminative models, such as the waveformer and the audio sap. These models capture the conditional probability between the input and output. So this model can often get a very good extraction from the mixture audio and with good signal quality. The best thing is when it comes to some overlapping regions, which means we have multiple sound events happen together. This model often fail to extract the clean sound from the. Another way is by using the generative models like the diffusion TSE and the flow sap. These models can get a very good purity at the overlapping regions, but sometimes it cannot locate the sound very well. And also the signal quality is not as good as the discriminative models. Well, for the reference information used for the TSE, there are many ways, including some sound-related clones, like the reference audio or a reference speaker, like that. And also some people started about the visual clones by using some pictures, or the natural language clones by using some text. There is a key problem for the TSE that we want this model to have the zero-shot abilities, which means if a new sound event comes, we want the model to handle this, not just in the inside data. We also want to do it in the outer domain data and unseen levels. Well, for the training materials, most people will use the free sound dataset. There are 41 categories with very clean single label audios. People use them to simulate the mixtures and train the model. Another way may be using some large dataset, such as the audio set. There are many multi-label sound clips. But a problem here is if we use such dataset, we don't have a ground truth of the single label. So the model is trained to get the extraction of multi-label targets. When we come to the real application, like we want a single sound event, these models cannot get very good results. So to overcome these problems, So in this work, we study both the audio-oriented and the language-oriented, which can be easily transferred to the unseen labels or out-domain labels. And we want to improve the performance of the generative model. So in this work, we propose a more efficient network with a transformer backbone with escape connections. This transformer model, we apply the diffusion process in the latent space from an audio VAE model. And we explore the synthetic data to train the TSE. In which we use a text-to-audio generation model to generate some clean single label data, and then we use this data to train the model. And the main goal is to test its generalization abilities, and we found it's good to the out domain data and show very strong zero-shot and few-shot abilities. First, we go through the methods about the diffusion models, which includes a forward and backward process. We can define the forward process in this equation that given a clean signal x0, we will gradually add some noise epsilon into the clean signal and form the noisy data st for each time step. In the forward process, we will add noise step by step. And here we can calculate the SNR according to the S0 and the XT by this function. We use a popular variance schedule that is used in the stable diffusion. It's defined in this way. But when we do this, we found that if we goes to the first state, which means the capital T time step, we can calculate the relationship between S0 and XT with this equation. As you can see that it's not a purely Gaussian noise at the start time. So, but we are using it to train the first step. So when we go to the inference, we don't know what the x0 is. So there are some mismatching between our training and the inference. To overcome this problem, we apply the zero-shot SNR method by just simply keep the alpha 1 unchanged, and we change the alpha capital T to 0, and then we linear rescale the alpha T according to 0 to the alpha 1. And here, this is the original function here. When it comes to the capital T, by using such way, this part goes to 0 and this part goes to 1. So the S capital T equals to epsilon, which means at the start time, the model tries to estimate random Gaussian noise. So it's not very meaningful for our model to predict this. Instead, we will estimate velocity here, defined in this function. So the relationship between the velocity and xt is shown in this picture. When it goes to estimate the velocity, we can find that in the time step capital T, the velocity is minus x0. So it makes sense for our network to estimate such element. And here is an example that using the correct DPM method, if we do not change the change to the velocity prediction, there are some background sound always happen in the audio. This is what we don't want these parts. By using such way, we can get a much clean extraction from the mature audio. And then we go to our model part. The solo model relies on a transformer based model. Here we have three key parts here. The first is audio VAE, that we train a model directly from in the waveform domain to compress the audio into latent space. And second part is CLAP. CLAP is kind of like the clip. If you're familiar with clip, is just a model to align the text domain with the audio domain. And this one can be useful for our zero-shot abilities because we don't rely on a label. We rely on audio embedding here. And the main part is backbone is the DIT-like model. The DIT was proposed in the stable diffusion paper. It's kind of like the backbone is kind of like this with some adaptive layer norm and the multi-head self-attention in between of the blocks. The only difference between our DIT with the original DIT is that we add some landscape connections here. Because in our task, we sometimes we want the input and output be the same. So by using such way, the model converge can be faster than if we don't use this. And also we can get a better recovery of the input if we just doing the copy paste task. So in conclusion, given a mixture audio YM, we first go through a VAE encoder to get the latent features XM. And we have a reference information like we want to extract the sound of people speaking. We will go through a collect model to get the reference embedding XR here. And for the input, we also have the time step T and the current latent state XT to the model. And the model will give us the output of ST-1, which is the next state latent features. So by using some diffusion reverse process, we can get the clean sound X0. And then we use the VAE decoder to recover the original waveform Y0. During the inference, we also use another useful method called classifier-free guidance. Sure. Yes, and we can choose one of.
The audio current here is
Yes, you can use any other gunshot sound as the target. Yeah. Here during the inference, we use the classifier-free guidance same as the other papers that we combine the conditional sampling and unconditional sampling to guide the inference of our diffusion process. For the data set, we were using 3 candle data here. The first is we use the free sound data set to get some simulated mixtures, which have 41 categories. We set this as the in-domain data. And we also add some synthetic data by a text-to-audio model. We used a model called Tango to generate over 200 categories of sounding ones. And we use them to also get the simulated data of mixtures. As we can see here, there are some label overlapping here. We have 22 labels also happen in the FSD dataset. So these 22 were used to evaluate the out-domain data performance. And there are 19 labels not happen in both datasets, but only for the FSD dataset. We use them to evaluate our zero-shot abilities. We also test on real data because all the others are the simulated data. We manually choose 2 samples for each category and ask people to listen to the results. And we calculate several perceptual metrics to measure the difference or the similarity between the target sound and our extracted sound. And here, table 1 shows our in-domain evaluations on the FSD mix, which means we train on the FSD and then we test on the FSD. Comparing with state of diffusion method, DPM, TSE, our SoloAudio can get greatly performance gain compared with the DPM TSE. And we also found that the skip connection can not only speed up the training, but also give us better performance. We then started the influence of the CFG by setting different guidance scales, and we can find an optimal values of 2.5 for the audio-oriented TSE and 3 for the language-oriented TSE. So the setting is kept for all the other experiments. Furthermore, we compare the zero-shot and few-shot ability of the SoloAudio. As we can see in this table, we have 2 kinds of label, seen label and unseen label, which means we have 22 labels happens in both data set. So it's seen labels, but it's our domain data. And unseen label, which means we didn't see this during our training. And by comparing with the FSD with our Tango synthetic data, we can see that the synthetic data can give us a better performance comparing to the original FSD. And we then train the model on the Tango synthetic data and test the zero-shot abilities. When we go to the results, we can see that the model shows some good zero-shot abilities. If we just use one sample of each category to further fine-tune the model, the performance will greatly improve by the just one sample. And then if you use a small number of like 10 samples to fine-tune it, it's close to the original FSD results. And then we test our performance on the real data. So here we have 12 participants to listen to the audios of our audios. And we asked them to answer 2 questions. First, the extraction. Does the generative audio contain the target song as described in the text? Another question is the purity, that we asked them, does the generative audio only contain the song corresponding to the text description? We think that these parts are the main problem for the TSE task. And here we report the results comparing with some state-of-the-art models, including AudioSAP, which is trained on the much larger AudioSAP data. And the waveformer and TSE, we use the same setting as our experiments and trained on our data. The results shows that the SoloAudio can always get the best results, except the extraction, we get the second best results. And when we go to the AudioSAP, we found that it can get a very high extraction results, but with quite low purity. Yeah, the extraction is the extraction is does the target. Okay, so we don't need to repeat again. So when we go to the audio side, we found that the extraction is good, but the purity is quite bad, which means that it can it's just like a copy paste of the original audio, that it cannot reduce the other unrelated sounding ones from the mature audio. We have an example here.
Okay, so this style is characterized by its rhythmic content. So this style is characterized by its rhythmic content.
From the listening test, I found some problems happen in the SoloAudio, that although we can get a very good purity, but sometimes the audio quality or the recovery is not as good as AudioSAP. As we listen to this sample, the acoustic guitar, we may lose some details in the output. So here we raise a question: how can we further improve the audio quality or the recovery of this model? And then I'm glad to introduce our another work called the Fast Gecko that we published in the Interspeech 2024. So this model is going to enhance the signal quality produced by either a separation model or extraction model, which means we can further use this method to make our performance better, especially for the audio quality. So different from the enhancement task, this model is trained not only to reduce some noise, but to suppress the interference from other signals and the artifacts generated by the front-end model. To give you a brief introduction, the Gecko is just kind of like a diffusion model, which is trained to refine the output of separation model. So given the input of current state xt and S1 height, which is the predicted signal by another model, and Y is the minstrel audio, we want the Gecko to gradually refine the signal step by step. But there is a problem for the Gecko is, even though we can gradually optimize this, we cannot directly optimize the final stage, which is the X0 with our clean data. So to overcome this, we further design another way called Fast Gecko, that we directly goes to one of the step to the final step, and then we use a predictive loss to fine-tune the model, so that we want the model to better recover the audio quality. And also in this way, we can transfer in the diffusion into just one step. And we can listen to some audio samples here. Here is a mixture when we do the experiments on the speech separation.
Don't you know one about bacon and tallow candles? Can't you tell any?
And we want to get a woman's song.
Don't you know one about bacon and tallow candles? Can't you tell any? Don't you know one about bacon and tallow candles? Can't you tell any?
So basically, the Fast Gecko will refine the output from another separation model, and it often make the performance better. So in conclusion, we have proposed some generative model for the separation and extraction task, including the TSE and the speech separation. In the future work, we will test the Fast Gecko on our SoloAudio, which means we want the Fast Gecko to make the audio quality better of the SoloAudio. And we also improve the sampling speed of SoloAudio. Now we use 50 steps for the diffusion, but we found other generative model that which is much faster to sample. And then we will investigate the other text-to-audio tools. So the co-author Jerry has already published another text-to-audio, which is better than the Tango. So we may have the chance to test it in our pipeline. And others we can further use to explore other reference information, such as the images or some macro arrays, which means the direction of the sound. And all of our code and models have been released. If you are interested, you can scan the QR code. Thank you so much. Any questions?
Yeah, so I'm curious about separation, where it would be hard to do it locally, but there's more global information that helps you do it. So imagine you have I don't know, somebody singing a duet with himself. So you have two, it's the voice quality is the same.
Yeah, you mean
but the melodic line, if you think about like a language model of what they're singing, or they're doing a scale going up with one voice and some other pattern with another voice. Would this method be able to pick that up?
Yeah, there are some studies about this. Like, they will use the text information to guide the separation, because they usually speak two different kind of natural language. All the content, they are different. So some people may use LM at the end to guide the separation, like what you said.
But your method doesn't have a place to put an LM in it.
Yeah, we can do this. It's a different thing, because what we can do is we get the results from this model, and we can set up another loss, like the text or the ASR loss, the speech recognition loss, to get the contents of different speakers. It's kind of like this. These content are the global information totally. So if we set up another loss with the content of the speakers, so we can also use in our model. Yeah.
No, very example of, I think what Jason's looking for is, imagine if you have two guitars. And you're extracting separately.
Yeah, each one is playing a different, one's playing melody, one's playing harmony.
Right.
But I think Helen already covered this by having two people saying, or the same person saying different sentences fixed.
No, that's a little bit different, because we rely on text, on a transcription. Whereas what you're saying is, in the case of two guitars, the global information is in the melody, and the fact that one is playing harmony.
Right. So the reason I thought it was analogous was I assumed we didn't know the text. You just wanted to separate into two things, both of which were fluent sentences that scored highly under the element. Helen, did you mean you were given the text, or you just scored the separation using a language model?
Yeah, we can do not use the text. We can even use some self-supervised features to guide like it's not, we don't need a text. We can use some other latent feature, like people do the
So this should apply to melody and harmony also, because you have a language model over sequence of notes.
Yeah. For the guitar, if it's all the same instrument, now the model can only get the output of both. But if we can design more, if you want, if you have other applications.
So in order, you need to train that model on audio that's already been separated. So like the language model is trained on not on overlaid sentences, but on individual sentences.
Yeah, we have the target.
That's the thing. So in the same recording, sometimes you have the two instruments playing Papa and you can know that part. You can use that to part them over. In the same recording, the same.
Are you saying that you adapt the language model to the figures that they play individually?
Yeah.
Well, so one interesting question then is whether if you applied that method to a fugue, like a lot fugue, it would pull out the different different lines that are interleaving, because they're often found separately. You need a model that does some memorization for that. That's how I'm using it. Would analyze it.
Thanks.
And I think you started this project and your colleague in the class, right?
Yeah. No, in the visual deep learning class. Yeah. Yeah, we have another work. Yeah. This is the second version.
For students, don't take public classes as like as nothing really. Can go far. All right. Any other questions? No. now the individual solves and the million
Can you answer that question?
Sorry. Sorry.
because the data,
Mm.
so when
Yeah.
the cicadas come out, there are thousands of them, and each of them will make the sound.
Yeah,
And then
it's not very often. Yeah.
there's more fishermen.
I'm sure cicadas come to the black. They come to the.
What I'm thinking is the cicadas might offer it to low power. What's that?
All right, thank you guys.
Thank you.
Thank you guys.